Hi, this is Tzvi Rosen with another lecture on the history of calculus. And today's lecture is going to focus on Bernhard Riemann, another great. Let's pick up, though, historically, in terms of the history of math, with a lingering question. So in previous lectures, we saw how Euler made functions the central object of calculus. And then Cauchy made limits the essential tool of calculus, using limits to define continuity, derivatives, and integrals. But Cauchy's definition of the integral required the function to be continuous on the interval ab. Is this a reasonable restriction, or does the definition need to be adjusted to allow more flexibility in what functions can be analyzed? Let's start by considering what types of discontinuities we can encounter. The first are piecewise continuous functions. These are finitely many discontinuities in an interval. And an example of this is the function parentheses of x. This is the distance of x from the nearest integer. So the formula for that would be x minus the rounded version of x. Let's graph a bit of this function. So we'll get the y-axis and the x-axis. Okay. Now, if we're drawing the value of this function starting from 0, so as we get larger, we just get the decimal part of x. But then once we hit x equals a half, we drop down because now we're subtracting the integer that's ahead of us. Okay, and then once we hit that integer, we keep going, but then it'll repeat. And we do have periodicity here because our position relative to the nearest integer is all that's important, not the absolute value. Okay, and because half rounds to 1, the value at a half is going to be negative a half because we have a half minus 1. Okay, and so we have an empty circle here indicating that that's not the value that's actually being taken. And a closed circle here. Okay. In terms of how we would deal with integrals here, so let's say we want to take the integral from 0 to 2. So for that, so let's say we want 0 to 2 x dx. Well, even if we're thinking about just using the standard continuous integral that Cauchy defined, we can still deal with this in a pretty simple way. You just have to kind of stop every time you hit a discontinuity. So you could make this from 0 to 1/2 x dx plus the integral from 1/2 to 3/2 x dx plus the integral from 3/2 to 2 of x dx. And on each of these pieces, the function is continuous, and we don't have to worry about discontinuities. We can just use the Cauchy standard definition. However, infinite discontinuities in an interval are also possible. And let's see an example of this. This is Dirichlet's function, and Dirichlet was a teacher of Riemann, we're going to see. But he defined the function phi of x, which returns 0 if x is rational, and 1 if x is irrational. And the claim is that Dirichlet's function is discontinuous everywhere. So let's first draw the function that we're looking at. Problem is that it's very difficult to draw. Okay, because no matter at what scale you're looking, you're always going to find some points that take the value 1 and some points that take the value 0. Why is this discontinuous everywhere? Well, it's because both the rationals and the irrationals are dense. They can be as small and as closely packed together as you want them to be. And that means that if you have x rational, it's not hard to write a sequence such that the limit of the terms is x, but for any n, an is irrational. Okay, and the fact that that's irrational means that the value of your function at every point of the sequence is going to be 1, but at the limit of the sequence it's going to be 0. By the same token, if you have x irrational, you can find a sequence such that the limit of that sequence is x, but every term in the sequence, Bn, is rational. Okay, that explains why it's discontinuous. So this is a discontinuous function. Should we be able to integrate it? You know, it seems kind of weird if we would be able to, because there's kind of this haze of points floating at 1 and this haze of points floating at 0. So going into this lecture, we have a sense that continuity is a useful tool in being able to integrate something, but maybe it shouldn't be necessary. Maybe it should be. We'll see. That brings us to our protagonist, Georg Friedrich Bernhard Riemann, though he was generally known as Bernhard Riemann. He was born in 1826 in Breslau in the Kingdom of Hanover, which was one of the states in the German Confederation, and it was controlled by Great Britain. His father was a minister, and he went to university to study theology at the University of Göttingen, but he switched to math to study under Carl Friedrich Gauss, one of the greatest mathematicians of all time, who was teaching there at the time. After making the switch to math, Gauss encouraged him to go to Berlin to study with some colleagues of his, and he went there for 2 or 3 years to study under Dirichlet, Jacobi, and Steiner. Then he came back to Göttingen. Eventually he would become a professor at the University of Göttingen. Dirichlet, who went and took over Gauss's chair in Göttingen, became a professor there, and Riemann eventually took his seat. Then, during the Prussian conquest of Hanover, Riemann fled Göttingen, and during that trip he sadly died in Silasca, Italy, of tuberculosis at the young age of 39. And the fact that we're talking about him despite his death at such a young age tells you what the magnitude of his contributions were. So here are a few things that Riemann contributed to the mathematical world. The first is perhaps what he's best remembered for is Riemannian geometry, the study of higher dimensional manifolds, extension of a lot of the geometric ideas of Gauss to higher dimensions. He also made huge innovations in complex analysis. For example, the Cauchy-Riemann equations are named after him, as well as the Riemann mapping theorem. He was huge in number theory, and the Riemann hypothesis is perhaps the most famous open problem in mathematics, describing the distribution of zeros of the zeta function. He also pioneered some ideas of topology in its early phases, like connectivity and genus. But what we'll talk about is Riemann's contribution to calculus. In particular, he gave a number of new tools for series analysis, and he defined the Riemann integral, as well as advancing Fourier analysis and other things. Okay, so let's get back to Riemann's take on the integral. Just to review, we had this question about should we require a continuous function in order to integrate it, or is it possible to define the integral without that continuity? So Riemann defined the integral this way. we start with a partition of our interval. So if we're taking the integral from a to b, we need a sequence of points between a and b. And then we're going to name delta. Delta I will be the difference between xi and the previous point in the partition. Okay, then we're going to choose values epsilon I in the interval 0 to 1, and we're going to define s equals delta 1, so this length, times f of a plus epsilon 1 delta 1, plus etc. Okay, similarly, always multiplying the width of that interval. Okay, so if we were to take, let's say we had the integral from, we're trying to take the integral from 0 to 5. So we would have, let's say, x1 is here, maybe x2 is here. It's not required to be even. x3, x4, and x5, and then we have our a and b. This is our b, this is our a. Okay, and so then our delta will be here, delta 1, delta 2, and then f of a plus epsilon 1 delta 1, all that's saying is take some point in this interval and take the y value of its of the function at that point. Okay, and then what we're adding together at each of those stages is the area of the rectangle whose width is the width of the interval and whose height is determined by that function value. Okay, so we could take this, we could take this function value to get this rectangle. And perhaps you can see this won't be a very good estimate because inside of each of these intervals, the values are going to be shifting a lot. But this should make you remember Cauchy's definition, which was very, very similar. He used essentially the same formula and the same limiting operation. So how is the Riemann integral different? Well, Riemann's definition, he said the following. If this sum has the property that however the delta k and epsilon k are chosen, it becomes infinitely close to a fixed value a, as the delta k become infinitely small, then we call this fixed value the integral from a to b of f of x dx. If the sum does not have this property, then the integral has no meaning. This should have f of x in there. And this translation is due to or is cited in William Dunham's book, The Calculus Gallery. Here, Riemann diverges from Cauchy, allowing for the possibility that the integral exists even if f of x is not continuous. Okay, so this limit, Cauchy observed that this limit exists when the function is continuous, but it might exist even when the function is not continuous. Okay, and to understand when this limit will exist, we're going to look at how far apart two of these Riemann sums can be. So for a fixed partition and different choices of our epsilons, meaning choosing the function value, how far apart can two approximations for S be? Okay, so we'll go through picking the largest value that a rectangle can have and the smallest value that a rectangle can have, going into the negatives. So first, the largest value. So we're going to basically be taking the rectangle which hits the highest point associated to every associated to the function in that interval. Okay, so obviously the lines I'm drawing here are not reflecting all of the oscillation of the functions inside of these intervals. Okay, that's the highest point for this interval. The second peak is the highest point for this interval, so we'll draw it about there. Oops. And this one goes up to here. And we're just going from 0 to 5, so that's all we would need. And So then the associated area would be these shaded regions. Okay, that second rectangle is 0. Okay. How about the smallest possible value? Okay, well, let's draw this with, we'll use red. Okay, so this can go as low as this. Here we're going as low as that. And this one dips even lower. This one has lowest value here. This one has lowest value here. Lowest value here. Lowest value here. Okay, so this is going to be a very different Riemann sum. Okay, so the first interval looks like a 0 value. Okay, so to summarize, it looks like the difference between these two estimates is basically the area of the rectangle, which has the width of the interval as one dimension, and the difference between the max and the min of the interval as the other dimension. So, oops. So something like this area, this area, this area, this area, etc. Oops. And this area. Okay, so this would be a very large error in approximating this integral. And if we want to get the integrals to approach a limit, we're going to need these error rectangles to get as small as we could possibly want. Okay, and the way we're going to do that is by defining these type A and type B intervals. So we're going to fix a partition similar to what we had in the last slide, and we're going to fix a maximum allowed oscillation, sigma, some real number sigma. Here I think I set sigma to be 1/4. Okay. Now we're going to check which of these intervals is type A and which is type B. So we're going to use this sigma ruler to compare to the oscillation within this interval. And it does appear to be less than sigma, so we're going to call this an interval of type A. Sorry, it should be it's an interval of type B. Okay. Now let's apply the same sigma ruler in the second interval. That definitely oscillates more than sigma, so this is going to be a type A interval. The next interval also oscillates much more than sigma, so that's type A again. This one more than sigma. This is again type A. This one, a bit of a closer call, but it's also type A. This one looks like it's just inside of the sigma, so this is type B as well. And the next interval, it oscillates much more. So here we have mostly type A intervals, which indicates why our approximation was quite so bad as it was. Okay, so Riemann's integrability condition was as follows. We're going to let S of sigma, okay, where sigma again is that permitted oscillation, S of sigma will be the maximum combined length of type A intervals for any partition whose largest interval has size at most d. Okay, so meaning we're bounding all of these little sub-intervals by d, and then we're counting how many of those subintervals is type A, and we're doing this for all possible partitions. Then the theorem of Riemann states that the integral from a to b of f of x dx exists if and only if, for any sigma greater than 0, we have that the limit as our permitted interval size, as that d goes to 0, the limit of the length of the type A intervals has to approach 0. Okay? So looking at this picture, as we cut up this graph into smaller and smaller pieces, okay, as long as those pieces are small enough, all of the intervals, there will be very, very few intervals where the oscillation gets to be more than, where the oscillation is more than sigma. The key idea being that the Riemann integral exists if and only if our oscillations can be controlled. Okay, so let's look at an example. The function that we mentioned earlier, Dirichlet's function. Okay, again, this is the function which is 0 for rational numbers. So we have a bunch of, we have a bunch of 0 values and a bunch of 1 values. So what Riemann's integrability condition says is we should be, if this is going to be integrable, then as long as we get this small enough, as long as we get the partition into small enough pieces, I should be able to bound the oscillation within any one of those intervals. Okay, but because the rationals and the irrationals are what we call dense, meaning they're found in any interval, no matter how small, you're going to find rationals and irrationals. The oscillations can never be less than 1. Okay? For that reason, if sigma is 1, is let's say 1/2, just to make it clear, all of our intervals will be type A intervals, no matter how small our partition is. Small our partition is. Okay? And for that reason, this integral does not exist. So the Dirichlet function is not integrable. Okay. Cool. So we have an answer. According to Riemann, this function just cannot be integrated. But there are discontinuous functions that can be integrated. And Riemann produced a beautiful but weird example. So we saw the parentheses x function from before, the difference of x and the nearest integer. In other words, x minus round x, where you round up from 1/2 to 1, and otherwise just the closest integer. And we're going to define a new function, f of x, to be equal to the sum from k equals 1 to infinity of this fractional part, but of or this distance to integers of k times x divided by k squared. And you're summing that up as k goes from 1 to infinity. Okay, now to illustrate what that looks like, we're going to take a trip to Desmos. Here we are on Desmos. We'll start by looking at the parentheses function. This is the one that subtracts the nearest integer. And you can see that there's discontinuity at 1/2 and at 3/2, and basically integer shifts from 1/2. Now we can look at what happens when we add in a multiple, integer multiples of x. How does that change the resulting function? So when k is 1, f of kx is just f of x, so it's the same as before. But then when we multiply it by 2, now the discontinuities are at 1/4 and 3/4 and at half integer shifts. Okay? When k equals 3, now we have a discontinuity at 1/6 and then 1/3 shifts. Then when we have k equals 4, we have a discontinuity at 1/8 and then shifts of 1/4. Okay, and you can see how this continues, and you get more and more discontinuities as you add more terms, or as you take higher multiples of x. What happens as we divide this by k squared? Well, for k equals 1, it stays the same, and as k gets higher, the number of the location of the discontinuities and their number stays the same, but the magnitude of the function shrinks. Okay, so even though the discontinuities are becoming more in number, the severity of the gap lessens. Okay, and let's see how it adds up together. Okay, this takes the sum of all of those f of kx over k squared up to, and obviously we can't do infinite sums in Desmos, but we're taking partial sums, and if we take n equals 1, okay, going further, so it very quickly settles into what looks like kind of an S-shaped curve with lots of discontinuities, but again, it's at, there are a few very bad ones, but they get, the discontinuities become less and less severe after the worst ones. Okay, it also has kind of a neat fractal pattern. When you zoom in, it kind of looks how it looks from zoomed out as well. And if you want to think about what it might be like to take an integral, here is the region, between the x-axis and the graph, okay? And Riemann proves that this is actually an integrable function, but we'll get back to that. Okay, welcome back from Desmos. So we're going to claim that this function is discontinuous at every rational number of the form 2a plus 1, some odd number, divided by 2b, some even number, for any integer a and b. And furthermore, while f is discontinuous, it is integrable. Okay? We'll start by proving discontinuity. So we're going to let x naught be equal to 2a plus 1 over 2b. Okay, this is an odd number over an even number. We're going to claim that the limit as x approaches x naught from the left, the minus side of f of x, is not equal to the limit as x approaches x naught from the positive side, the right side, f of x. Okay? And the proof of that can be done by looking at the associated sum. So if we have, so f of x is equal to the sum of kx divided by k squared from k equals 1 to infinity. We'll consider the terms where k is equal to an odd multiple of b. Okay? So when k is an odd multiple of b, then 2n plus 1 times b times 2a plus 1 over 2b, that gives you some odd integer divided by 2, okay? Which is we call this 2c plus 1 over 2, and that's going to be the same as c plus a half. Okay? So then the limit as x goes towards x naught from the left of kx over k squared, well, when you're coming from the left towards a half, you're approaching a half. So this will be equal to 1 over 2k squared, whereas the limit as x approaches x naught from the positive side is going to be minus a half. So that's going to be minus 1 over 2k squared. Okay? And these disagree by 1 over k squared. And then when you add that up over all k, you get a gap, a jump of some amount. And that's where the discontinuity comes from. Okay, and that's what you saw in the Desmos demonstration. Okay, now we'll try to give a high-level proof of why this function is integrable. So let's say we fix sigma greater than 0. Okay, to prove Riemann's integrability condition, what we would need is the following. We would want to show that the limit as d approaches 0 of s of sigma is 0. Okay, again, this s of sigma is the length of the type A or bad intervals, meaning the intervals that are very highly oscillatory. Okay? And what do we mean when that the limit is 0? It means that, okay, equivalently, for some epsilon greater than 0, there exists d greater than 0 such that any partition with max interval size d has s of sigma less than epsilon. Okay, so we can give a fine enough partition size that any partition which is that fine has to have s of sigma below epsilon. That's, again, there's a lot of flying quantifiers here, but that's the outline of what Riemann's integrability condition seeks to prove. And for this function, the way that he does that is to say, well, really, there's infinitely many discontinuities, but to get discontinuities that are bad, that are like worse than some fixed size, then there are only finitely many. So let's say we want to highlight all of the bad points where the function jumps by more than 0.1. There aren't actually all that many of those in a fixed interval, right? So if I can avoid those points, or if I can assign a fine enough partition that just giving one interval to each of those bad points still doesn't get me all the way to epsilon, then I'll be in good shape. Okay? To show that we can do this, note that the jump at the point 2a plus 1 over 2b is bounded above by pi squared over 8b squared. Okay, and you can do this by computing the function precisely and setting an upper bound using the Basel problem. But having the b squared in the denominator here means that for b large, the jump is small. Okay? In particular, if b is greater than pi over the square root of 8 sigma, then the jump will not be enough to give you a type A interval. Okay? So as long as we can stay away from the denominators that are less than pi over root 8 sigma, then we'll be set. Okay, so we're going to get a type A interval for everything less than pi over root 8 sigma, at least theoretically. So as long as we're okay accepting those errors, then we can be happy with the remaining graph. Now let's define a number n of b to be the number of fractions in our interval with denominator at most 2b. Okay? And this has to be finite, assuming we're on a bounded interval, just because you can count all of the fractions. Count all of the, once you divide it up into 2b pieces, there's only 2b many fractions, let's say between two integers. So you're going to be in good shape. Okay, this is a finite number. Okay, then we can choose our d, the fineness of the partition, to be equal to epsilon over 2 n of b. Okay? Then, even if we get a type A interval, so all type A intervals from the jumps will give us n of b times epsilon over 2n of b in terms of the length, which is just epsilon over 2. Since that's less than epsilon, we'll be in good shape in terms of approaching 0. So we've got our sigma, we've got our s of sigma to be less than epsilon, meaning that it's approaching 0. Okay, and there's some subtleties to the argument here that I didn't go into. For example, you might get type A intervals that are not associated to jumps, but there you can just use properties of continuity in kind of typical ways. The key here, though, is that you can isolate the bad jumps in small intervals, and then the sum of those small intervals will stay pretty close to 0. Okay. That was a mouthful, but now we'll do something that's a little bit more palatable, and that's the Riemann Rearrangement Theorem. So another fun theorem that Riemann proved was the Riemann Rearrangement Theorem, which really illustrates how quirky series can be. So we're going to consider an infinite series, sum of ck, which alternates between two different positive series. So you start a1, then you take minus b1, plus a2, minus b2, etc. Okay, where both ak and bk are positive terms. And now we're going to suppose that that series is conditionally convergent. In other words, the series itself converges, but its series of absolute values, meaning a1 plus b1 plus a2 plus b2, etc., diverges. Okay, One not too difficult result to prove is that independently, the AK and the BK both must diverge. Furthermore, we can reorder the terms of the series so that it converges to any real number. Okay? That might be surprising if you haven't seen it before, because in the finite world, adding things up, it doesn't matter what order you add it in. Addition is commutative. But in the infinite world, that's not the case. Okay, so here's an example. If you have the series 1 minus 1 plus a half minus a half plus a third minus a third, etc. So added in this order, okay, it's clear that we're looking at 0 plus 0 plus 0, etc. And it should converge to 0. But what happens when we consider this rearrangement? 1 plus a half minus 1, plus a third plus a quarter minus a half, plus a fifth plus a sixth minus a seventh, etc. So what are we looking at here? Well, this, when we group terms this way, this series becomes 1 minus a half plus a third minus a quarter plus a fifth minus a sixth. Okay, and this is very similar to the Taylor series for ln of 1 plus x, which we know to be 1 minus x over 2 plus x over 3 minus x over 4, etc. Just plugging in x equals 1, this we get on the right-hand side the series that we're looking at, and on the left-hand side we get ln of 2. So this is ln of 2. Okay, cool. But it's not just like very special values that we can take. We really can get any real number value. And the idea of the proof is as follows. Okay, because you have an and bn, so an is the positive terms, and I guess, well, the minuses gives you negatives, and both diverge. But because the series is convergent, the terms get arbitrarily small, but terms approach 0. Okay, so each of these has kind of infinitely much matter in it, but arbitrarily fine constituent pieces. So what we can do is just add an until greater than desired limit L. Okay, that's our first step. Then subtract bn until less than L. Okay, and then just lather, rinse, repeat. Okay. We're always going to get higher than L because the ANs diverge to infinity. And we're always going to get less than L because the BNs diverge to infinity. But because those pieces are getting smaller and smaller, as we overshoot L, we're overshooting by less and less. Okay? And that was the Riemann rearrangement theorem. So just to summarize, Riemann was exceptionally influential despite his tragically short life. He extended Cauchy's integral definition to discontinuous functions by bounding oscillations. He also introduced the pathological integrable functions to demonstrate the usefulness of his definition, like the beautiful graph we saw in Desmos. Additionally, Riemann proved the rearrangement theorem, showing conditionally dependent series are sensitive to ordering. And overall, he strengthened the foundations of the calculus, paving the way to the modern era of analysis. He was really a remarkable figure. And in the next lecture, we're going to take a glimpse at set theory, which will give us the tools to eventually define an even more general integral, which can handle even more bizarre functions. Thanks so much.